space translational symmetry. And the corresponding Noether quantity is linear momentum E. Okay. And the generator also, the generator of space translational symmetry is also E. Okay. So generator of space translational symmetry also linear momentum operator. Second is second is rotational symmetry. And the generator of rotational symmetry is angular momentum. And the third one is time translational symmetry. Time translational. And the generator of time translational symmetry is Hamilton H. Okay. So generator of space translational symmetry is linear momentum. Generator of rotational symmetry is angular momentum. And the generator of rotational symmetry is Hamiltonian, or the total energy in classical mechanics, and in quantum mechanics the corresponding operator. Okay. So now we have to start about the, so we have to learn about rotational symmetry. Rotational symmetry. So what does it mean? Under any rotation with an arbitrary angle theta, the system remains infinite. Okay. So mathematically, suppose the coordinate of a system is initially at x, y, z, and after an arbitrary rotation, after any arbitrary rotation, it goes to net slow হচ্ছে কোনো প্রবলেম হচ্ছে কি বোর্ডে বলে আচ্ছা ঠিক আছে একটু অ্যাডজাস্ট করো and after any arbitrary rotation the coordinate goes to x prime y prime z prime. Okay. Arbitrary rotation means I mean suppose about any arbitrary axis and about any arbitrary angle. Suppose about any arbitrary axis directed towards n cap with an arbitrary angle theta. That means suppose a point is at xyz, suppose xyz, and this is the n cap direction, and after rotation about an angle theta, suppose this angle is theta, this angle is theta, it goes to x prime y prime z. Okay. So after this rotation the system remains invariant. That's why I am calling it the rotational symmetry. Okay. So for example, suppose you have a point with coordinate x, y, z, and after rotation about z axis with an angle theta, it will go to suppose x prime, y prime, z prime, and you know the transformation between these. This transformation is very familiar to you, which is x prime, y prime, z prime is equal to x, y, z. This will be cos theta, sin theta, 0, minus sin theta, cos theta, 0, 0, 0, 1. That means the z coordinate remains constant. As you are rotating about z cap axis or z axis, the z coordinate of the initial point will be same because z prime equal to z. But the x prime and y prime, that means the x coordinate and y coordinate will change up to x prime y prime, and it depends on the angle theta. Okay. So this is the specific example of rotation or coordinate transformation under rotation about z axis with an angle theta. But in general, this transformation you can say this is a linear transformation. So coordinate transformation under rotation is basically a linear transformation, because you know for any linear transformation you can define the linear transformation matrix. So for this specific example, you have such instance. Here the transformation of coordinate under rotation about z axis with an angle theta. This relation, you can express this relation in terms of this Jacobian equation. Okay, and this matrix, this is transformation matrix.
স্যার লিনিয়ার ট্রান্সফরমেশন কেন বললেন আরেকবার বলুন।
Sorry. Any linear transformation can be expressed as this. For any linear transformation, you can write the transformation in terms of some multiplication of transformation matrix, which is square matrix, with the initial coordinate. Okay. Any linear transformation can be written in terms of that way. Okay. So because for any linear transformation, all the new coordinates will be the function of each and every whole coordinate. So x prime will be the linear function of xyz, y prime will be the linear function of xyz, and z prime will also be the linear function of xyz. So that's why you can write in this way. That means suppose in details you can say x prime will be the function of xyz, and this is suppose linear combination of xyz. That means suppose I am writing r11x plus r12y plus r13z. So this is the symptom of linear transformation. Okay. Similarly, y prime will be function of xyz. So this is suppose r21x plus r. Similarly, z prime also xyz equals to r31x, r32y, r33z. So generally xyz prime equals to xyz. This is r11, r12, r13, r21, r22, r23, r31, r32. So this is the symptom. These are the symptoms of linear transformation. Okay. So in general, you can write this one. This is suppose this is x prime equal to rx, okay, where x prime is x prime, y prime, z prime. X is equal to x, y, z. Okay, x, y, z. So this is the transformation relation, and this R is the transformation matrix in general case. This is called the rotational matrix. Rotational matrix. So you can write this one. This relation can be written in the contravariant form. This is suppose xi prime is equal to xi prime equal to rij of x. Okay, forget about the covariant and contravariant rank. I am as it is the Cartesian tensor, so it does not mean anything. Because covariant and contravariant can be taken in same way. In Cartesian tensor, in three-dimensional case, that means in Euclidean geometry, covariant and contravariant will yield the same. So forget about the notation. Okay, but that means J is dummy index here. Okay, so you can express here. Suppose x1 prime. X1 prime will be R 1 x plus R 1 2 y plus R 1 3 z. So similarly for if you put I equal to 2, then x2 prime will be R1 R2 1 x 2 2 y 2 3 z. So all these three equations can be written in contravariant form. And Rij, the Ij element of rotational matrix. Okay, so x j prime sorry x I prime, right? X I prime equal to Rij x j. Okay, and this j is dummy index, right? So you can use the different dummy index also, Rik x k, because this is summation over k, right? This is summation over j. So you can use any different indices, it will yield the same thing. Okay. Okay. Now you know any scalar is invariant under rotation. Any scalar must be invariant under rotation. So surely the dot product of the position vector. So here the dot product of position vector means suppose r dot r. R dot r means x square plus y square plus z square. So in contravariant notation you can write this is xi because this is summation over I, that means x1 square plus x2 square plus x3 square, which is x square plus y square plus z square. Similarly in prime coordinate, that means after rotation, this is r prime dot r prime, that will be equal to suppose this is I am writing xj, and this is suppose xi prime xi. So as scalar is invariant under rotation, so xj that means r prime dot r prime and r dot r, that will be same. After rotation, before rotation, they will be same in numerical. So surely you can write xj prime, or sorry xi prime, xi prime xi prime equal to xj xj. Okay. Now what is xi prime? You can put the value of xi prime, which is rij xj and rik xk. I am using different values with different dummy indices for the value of xi and xi equals to xj xj. So this is rij rik xj xk, and this xj xk, this is dummy index. You can split this dummy index using some Kronecker delta. This is suppose xj xk into Kronecker delta z, because this k will be summation over k, and only j equal to k value will entertain the 1, otherwise it will vanish. So that means These are same thing. Xi, xj, xk, chronica delta jk, and xj, xj will be same. Now you can compare this. Comparing, you will find Rij, Rik equals to chronica delta z. So Rij is the Ij element of R matrix, Ij element of rotational matrix. So that's why you can write this one R transpose Ji. Okay, because Rij equals to R transpose of Ji. After transpose, uh, the row and column indices will be interchanged. So that's why RT of Gi and Rik, okay, is equal to chronica delta Z. And you know the matrix product rule. Suppose you are going to product A and B matrix. So the product of AB, okay, the element of product AB, suppose AB element, that will be uh, A MK into B, sorry, I have to write this way, A B MN, and this is equal to A MK into B. This is summation over K, and as K is dummy index, we can drop the summation notation due to the Einstein summation context. So surely now this portion is actually the jk element of R transpose. Equal to 1. Okay, is this okay? Okay, so a matrix having jk element is equal to the chronica delta. That means this matrix only has the diagonal element. So R transpose R, this is itself a matrix, has only diagonal elements. R transpose R is a diagonal, has the only the diagonal elements, because chronica delta jk, j equal to k will yield to 1, otherwise it will yield 0. So R transpose R has only diagonal elements 1, and off diagonal elements will be 0. So that means as you are writing in 3 cross 3 dimension, so R transpose R, this is equal to I3. I3 means such matrices 1 0 0 0 1 0 0 0 1. Okay. And in any other dimension, suppose in 3D you can write in that way, in any other dimension R transpose R will be In, in n dimension it will be. So the property of rotational matrix, this is the signature of rotational, signature of rotational. And you know such matrices are of special kind. The matrices which follows this property are called, the matrices which follows this property is called orthogonal matrices. Okay? Orthogonal matrix. Any orthogonal matrix O transpose O will be R. This is the property of an orthogonal. So rotational matrices are basically orthogonal. So suppose I am denoting the set of n-dimensional orthogonal matrix, n-dimensional orthogonal matrix to be ON. This suppose ON. So you can say that this R that will belong to O3. Okay. So the elements which are basically can be treated as the rotational matrix will be the elements of orthogonal matrix here in 3D. Okay. Now look at the property of any orthogonal matrix. Suppose this has R transpose R equals to R. So you can say that the determinant remains same after transposition. If you make the transpose of a matrix, the determinant will not be effective. So you can write uh, this is matrix R, and the determinant of matrix R square is equal to 1 because determinant of unity matrix is 1. So determinant of R is plus minus 1. So we may have different results for orthogonal matrices. Some orthogonal matrices have positive, unit positive determinant, and some have a negative one determinant. So the elements of ON having unit determinant can form a group. This can form a group because this will satisfy the four properties of groups, and these groups are namely SON, special orthogonal. These are special because these have the unit determinant mod of R equals to 1. But the other elements which have the negative -1 determinant, they cannot form a group. Okay. So they are not special. Okay, so we have a set of rotational matrices which is ON. Amongst them, one is SON. SON having a determinant equal to +1, and others they are not so special. They cannot form a group because their determinant is -1. So generally, both of these elements can correspond to the rotation because these are the outcomes of rotational symmetry. Okay. But this special type of rotation, these are called the proper rotation. These are called proper rotation, and these are improper rotation. Okay, the proper and improper. Uh, for proper rotation, you have the determinant equals to -1. For example, parity. Parity in 3D, you know the parity transformation. X, Y, Z, it will go to -x, -y, minus. So you have -x, -y, -z. It is equal to x, y, z, -1, 0, 0, 0, -1, 0, and 0, 0, -1. So here mod of R equals to -1. So parity in 3D, it's a improper rotation. It is a rotation, of course. You can find the orthogonal matrices which are belonging to O3, but they are not proper rotation. It's improper rotation. But parity in 2D, parity in 2D. Parity in 2D, suppose we are suppressing Z axis, so x, y will go to -x, -y. So you have -x, -y equals to -1, 0, 0, -1. So here the determinant is 1. So parity in 2D is proper rotation. In 3D it is improper, but 2D parity. Okay, so these are the primary introduction to the rotational symmetry. Now, precisely, we are going to find the some other aspects of this rotational symmetry. So, in specific direction, that means suppose we choose the coordinate axis as the rotational axis. So, rotational axis, we are choosing the coordinate axis to be the rotational axis. So, x axis, y axis, z axis, uh, three orthogonal rotational axis you may consider. So, under rotation about z axis with an angle theta. Okay. And already we have found this one. The form of this one is cos theta, okay, sin theta 0 minus sin theta cos theta 0 0 0. So this is the rotation about z axis, the rotational matrix whenever the rotation is about z axis. Now consider the infinitesimal rotation. What do you mean by infinitesimal rotation? The rotation with very small angle. Suppose in the place of theta we are using delta theta to be the rotational angle. And here this delta theta 2 is very small. Delta theta tends to 0. It infinitesimal angle. Okay, but infinite number of successive infinitesimal rotation. Infinite infinite number of successive infinitesimal rotation can produce a finite rotation with angle theta. That means suppose initially the system is here, you are making small angle rotations. Okay, this is delta theta, again another delta theta, again another delta theta. So after as delta theta tends to 0, it's very small. After infinite number of successive rotation, you may find some finite rotation. Okay, that means theta is the finite rotational angle, which is limit n tends to infinity n into delta theta. Okay, so infinite number of successive small angle rotation will yield some finite and appreciable angle of rotation. Okay, you can make small successive steps to find a big success. Very small successes will make a big difference, a big success in your life. So similarly, you may find uh, very small angle rotations, and after successive rotations, you may find some finite angle rotation. But the repetition should be very high, 10 tends to infinity. Or reasonably, you can write delta theta is limit n tends to infinity theta by n. In other words, if you divide some finite angle rotation to be infinite number of equal portions, you may find some infinitesimal angle of rotation. Okay. However, if you put this one, which is delta theta tends to 0, you will find cos of delta theta. As delta theta tends to 0, cos of delta theta tends to 1, and sine of delta theta will tends to delta theta. So uh, here you can write, suppose r of z cap delta theta will be 1 delta theta 0 minus delta theta 1 0 0 0. Okay. And effectively you can write this is 1 0 0 1 0 0 0 1 0 0 0 1 plus I into delta theta, this is 0 minus I 0 I 0 0 0 0 0. Okay, you can write this infinitesimal rotational matrix about z axis in that, and this is I in 3D, this is I3, or I am writing I, simply dropping the dimensional index. So this is I plus I delta theta, and this is a matrix. This matrix is a Hermitian matrix, and this Hermitian matrix, this is I am writing, this is JZ. Okay. Now the question is why I am writing in that way? Because uh, you know, in quantum mechanics, any dynamical observable or the corresponding operator should be Hermitian. Why? Because in the mathematical tool of quantum mechanics, you have already learned the eigenvalue, the value or values of a Hermitian operator, each a real, and the eigenvectors are orthogonal. So these are the properties of a Hermitian operator or Hermitian matrix. So if we want to allow to describe this condition, allow to describe the rotational scenario to be related with some quantum mechanical operator, we must express it to some Hermitian matrix form, so that you can associate this its physical significance with some quantity which can be used in quantum mechanics as the operator. Okay. And if you clearly examine this one, you may find these matrices are the elements of Z. These are the elements of Z. I am writing JZ because if you can remember the matrix form of the angular momentum operators, this is surely the Z component of angular momentum Z. So we have the correspondence between rotational symmetry and the angular momentum. And this is obvious because already we have studied about the generators of symmetries. And already we have found the generators of rotational symmetry is angular momentum. So it is not a new thing to find the inclusion of some generators element in the rotational matrix, the transformation matrix of rotation. So, however, the R of z cap delta theta is equal to that. So, similarly, you can find suppose Rx, R of suppose x cap of delta theta. You will find the same thing, which is I plus I delta theta of Jx. And I of delta theta z. Okay. And where you have the formal form of jx and jy. Jx is suppose 0 0 0 0 0 and 0 minus I, 0 minus I 0. Similarly jy, look at carefully, as it is jx about the x axis, so you have to vacant or you have to put 0 in the x column and x row. X row and x column will be 0. So here y column and y row will be 0 and sit minus I. So this I and minus will be alternatively displaced. So this minus I will go to x and this I will go to z. So this is the form. These are the forms of jx, gy, zz. Okay. So for infinitesimal rotation, okay, for infinitesimal rotation, you have the rotational matrix, which are expressed as the linear combination of some unity operator, which is a trivial matrix, and the generators. Jx, jy, zz are the generators or the components of generator of rotational symmetry. Okay. Uh, Now, already we have found that the successive number of infinitesimal rotation, it will yield at last the finite. Okay, that means suppose you are making infinitesimal rotation in very high number of times, large number of times, you will find some finite. So here you can write, suppose r of z cap theta, it will be uh, r of z cap of delta theta and those to the power. Yes. And of course this n should be very high. So after successive infinitesimal rotation, we will find some finite rotation of theta. And here you can put r of z theta, which is I plus I delta theta, right? Delta theta means theta by n into jz 1 to the power n. And as this is n tends to infinity, it will yield some exponential series. You can search about that, the power form of exponential series. So this is one form of the exponential series, and it will yield e to the power I jz of theta. Okay. So we have already found the matrix element of R z cap theta, but in operator form you have this is R of z cap, the operator. Okay. So similarly about x and y axis, you can do the same thing, and you will find e to the power I, suppose jy of theta, and jx of theta.
এটা এখানটা আরেকবার রিপিট করুন। ওই
কোনটা?
টু দি পাওয়ার আই জেড জেড এটা যেটা হ্যাঁ
না মানে এইটা এটা actually this is the known form of exponential series. You can write this one as e to the power I z.
আচ্ছা
You can check in Arpken Weber Arpken book for this series, or you can Google it. It's very known form of exponential series.
ওকে স্যার।
So in new slide, you have to do a new slide. So similarly for the x and y axis, suppose x cap of suppose theta x or psi, it will be to the power I j x psi, and r of y cap of suppose phi is to the power I of j. It's an operator form of the rotational. It's quantum operator form because these jx, jy, these are quantum operators. In classical generator form, it was just only classical numbers. But now these are the operators which are the matrix form. Okay. Now in general, suppose we are choosing any arbitrary axis n cap and with an angle theta. Now this direction, you can write this direction as nx, nx, ny, nz, and theta may have been in components. This is theta is equal to suppose theta x, theta y, and theta z. Okay, so in that way, you can express this r of n cap theta. This is e to the power I jx theta x. Okay, that means you can write this way: jx nx plus jy ny plus jz nz of theta. Okay, suppose we are dropping this one because theta is just an angle of rotation. For the time being, we are not worried about it. So you have the form of rotational matrix operator in terms of jx, jy, z, and surely you will find this j, jx, jy, jz are the generators of Rn theta, are the generators of Rn theta. Okay, you can generate this group, okay, because these are the elements of SO3, right? These are of n cap theta, which belongs to SO3. Okay, rotational matrices, and these matrices can be generated by this jx, jy, jz with arbitrary angle theta. That's why these are the generators. So the generators group of SO3, the generators group of of SO3 is the generator group elements are jx, jy, jz, and you know the matrix form of this jx, jy, jz. These are known, and if you try to find the commutation relation of this jx, jy, jz, you know the commutation relation. J, 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 K is equal to I extra J, K, L, J. So the generators or the elements of generators group follows this commutation relation because they are non-abelian. They are not abelian. Each group is non-abelian. The elements of abelian group are commuting to each other. Okay, and the elements of non-abelian groups are non-commuting. These are not commuting elements. So this group is non-abelian.
তাহলে স্যার যারা সিএসসিও ফর্ম করে তাহলে সবাই অ্যাবেলিয়ান গ্রুপ।
CSCO may not form the groups also. Okay, suppose H L square and LZ. These will form the CSCO, but they are not group. L square, the elements of L square, they come from the different group. LZ is from different group. And if they satisfy the group, they may be the abelian. But they cannot satisfy the group in all time. Okay. So the elements of CSCO, because CSCO is not a group, CSCO is just a set of operators, complete set of commuting observables, not the complete group of commuting observables, right? CSCO, what does it mean? CSCO, CSCO is complete set of commuting observable. So clearly they have the commuting property, but they may not have the properties of satisfying a group. Otherwise, it may have the name complete group of commuting objects. So not CGCO. This is CSCO. Okay. Okay. So these are the generator group of SO3. They are non-abelian. And this particular form of non-commutation, that means this particular form of non-abelian groups are known as the Lie groups. These are Lie groups. So Lie group satisfies such, suppose the elements of Lie group be L. So LJ, LK, it will be I, EPSA, JKL, LL. So this signature commutation, non-commutation of Lie groups. So the elements of SO3, or sorry, the generators of SO3, they will form some non-abelian groups, and this is known as the Lie group. And that particular algebra is called the Lie algebra. The algebraic structure of Lie groups is the very familiar Lie algebra. Okay, so these are not commuting. Okay. Very interesting thing, because suppose at first the body is at here and the axis is coming out of the page or coming out of the. Now you are making some rotation about this axis with an angle theta. After that, you are making another rotation with phi. Okay. So if you change the order, that means at first you are making theta rotation, then phi rotation, or at first you are making phi rotation, after that theta rotation, or you are making one rotation with theta plus phi angle, so phi plus theta or theta plus phi angle. The outcome should be same, right? Is it okay? First make the rotation with angle theta, then phi, or first you make the rotation with phi, then theta, or you are making one rotation with an angle theta plus phi. Those will be identical. Okay. So mathematically, uh, it should be followed that r of n cap theta and r of n cap phi, this should be equal to r of n cap phi and r of n cap theta, and that should also be equal to r of n cap theta plus phi. That must be followed by the rotational matrix if you think in physical ground. Otherwise, it will not justify the reality. But if you look the expression of, if you look the expression of this one, expression of r of n cap theta, it is e to the power I jx nx plus jy ny plus jz nz of theta. Now this jx, jy, jz are not the abelian quantity. They are non-commuting. So that must not be sure. You cannot guarantee that these two will commute because the generators are not commuting. Okay. So how can you interpret this one? How can you interpret these things that as it or in spite of the generators to be in non-abelian group, these are the abelian. Okay, the things these things are very interesting. R of n cap theta. This is abelian. Okay, that means SO3. This is abelian. But the generators of SO3, which is small SO3, small SO3 is the generator group of SO3. This is non-abelian. So this makes the topic very interesting. A group which is abelian, but the generator of this group is non-abelian. Okay. So how can you interpret this? Right. So that must not be followed. Essentially, that must not be followed from that. Okay. The answer is, do you think the angular momentum are vector? Is angular momentum a vector quantity? Is angular momentum vector? Actually not. Why? Because any vector can be written in the row or column matrix. Suppose R vector.
আচ্ছা এদের 9টা করে কম্পোনেন্ট থাকছে
But now for Jx it's a square matrices. E cross 3 matrices. So these are essentially not matrix. Another thing, any vector will be just changed, will change its sign under parity. Okay, suppose any vector R under parity it will yield minus R, right? But if you look at carefully, the elements of J does not flip under parity. Okay. So J are not essentially satisfy the property of vectors. But one more thing is very important. The transformation of J are identical to the vector. So J is not a vector, not an ideal vector. But it transforms like a vector. So as J transforms like a vector, so this can be written as the dot product of J and N. Okay, you can write this one as the dot product of J and N. And this dot product will act as a scalar, and this scalar will be abelian, right? So that's the key. That's the key physics behind this rotational transformation. That angular momentum is not an essential vector, but the transformation of angular momentum under any coordinate system to another, it will be like a vector. Okay. So this is the rotational symmetry. So we have the generator group SO3. SO3 has the generator group small SO3. Okay. The elements are Jx, Jy, Jy, and Jz. and this generator group follow the Lie algebra. The non-commutative relation, Lie algebra. Okay. So the standard form of Lie algebra is special unitary group. Standard form of Lie algebra, SUN. Okay. Especially if you choose the SU2, SU2, this the elements of SU2 is identical to the elements of SO3 in terms of their generators, Lie algebra. Okay. And special unitary group has the identical properties of the generators of SO3. But one difference is that SO3 is orthogonal group, but SU2 is not orthogonal. SU2 is unitary. Okay. So SU2. So SO3, it has e to the power I JZ, sorry, J dot n cap of theta, and the elements of J that belongs to small SO3. Similarly, in SU2, the elements of SU2 can be written e to the power I. The generators are denoted as sigma. Okay, so this that should be sigma dot n cap theta. Okay, sigma dot n cap theta, where sigma belongs to sigma x, sigma y, sigma z belongs to small SU2. And you know the sigma are the Pauli matrices, which represents the spin dynamics of electrons, okay, or the spin of particles. Pauli matrices can represent the spin of particles rotation. But this rotation is not the physical rotation. This rotation, you can say these are the abstract rotation. These are intrinsic property of the system or intrinsic property of the fundamental particle, which cannot be observed directly, okay, directly from the dynamical point of view. These are the intrinsic property. So for convention, here half is cut, is multiplied with the generator. So in general, SU2 is e to the power I h cut by 2 sigma dot n cap of theta. Okay, so these are the elements of SU. Okay, so as half is associated with it, okay, as half is associated with it, suppose theta goes to 2 pi plus theta. Okay, theta goes to 2 pi plus theta. The elements will be same. So 2 pi angle of rotation. Okay, 2 pi angle of rotation will yield the same element in SO3, because e to the power twice pi I is 1. Okay, so e to the power I j dot n cap theta equals to e to the power I j dot n cap of theta plus 2 pi. Okay. For SU2, this is not same. For SU2, e to the power I h cut by 2 sigma dot theta, it is not equal to e to the power I h cut by 2 sigma dot, or in general sigma dot n cap theta. N cap theta is sigma dot n cap theta plus 2 pi. because e to the power I pi there will be there. E to the power I pi will be minus 1. Here it will be e to the power I twice pi, which is 1. So this will flip. This will not yield the same element. So twice pi angle of physical rotation is the obvious symmetry, is the trivial symmetry. But twice pi angle of abstract rotation, it is not same. So if you make some correspondence, between SO3 and SU2, that means physical rotation and abstract rotation, here you may have two elements which will correspond to the same one element in SO3. Okay, this is 360 degree rotation. So one making 360-degree abstract rotation will do, those are two different elements which will map into the same element, which will map into the one element in SO3. And physically it is also justified, because you know for spin half particle we have two rotations. One is spin up and another is spin down. It's up and down. Okay. And for angular momentum, orbital angular momentum, this will be same. So these are the mapping between SO3 and SU2. So most of the properties are same between SO3 and SU2, but there is one difference. The difference is very clear. So these two sets are not the isomorphic set. Any two isomorphic set has all the properties are identical. But here one different property which is not same. So these two sets are homomorphic set. SO3 and SU2 are homomorphic, not isomorphic. They are homomorphic. Okay. But their common thing is the Lie algebra. So you can study them by grouping the elements. So you can generally study any particular group which can represent both SO3 and SU2, and also in higher dimension also. You can study in general SUN. And studying these things, you can uniquely study all of these things. You don't need study the different cases for different groups. You can study the one Lie algebraic structure, which is supposed for SUN. Then you can access or you can analyze all of these things. Okay. So in the next class, we should follow the SUN algebra, or basically the Lie algebra with the root diagram, with the Young diagram. Okay. And in the light of group theory, you have already studied the group theory in the previous classes. So following the group theories, you can tally all of these things.